Hello, so here we go. This is all about transformations of graphs and polynomials rather, specifically of cubic and quartic. Unfortunately, they follow the same rules as everything, and as you remember, this is the main rules for it. And the easiest part of it are the y. I know this. I know the books. They always look like complicated. But I'm going to, in green, put the y transformations, which are the easiest ones. And actually, yeah, I forgot the plus c right here. And those are the easiest transformations, because exactly what you see is what's going to happen. So when there's a number here that's bigger than 1, 1 plus, it's going to be a stretch. When the number is between 0 and 1, it's going to be a compression. And then when the number is negative, even though this is a y transformation, the reflection will be in the x-axis. So if you had something like this, it's suddenly going to go to this side. And be aware, the x-axis isn't always exactly where it's reflected. It's usually reflected on its new line. So if it's 3 up here, and it gets reflected, it's going to be reflected around that C number. And what does the C do? It raises the whole graph up or down. So y transformations are exactly easy to figure out. And then the complicated stuff, of course, is the x transformations, which I'll do in red here. Is this k and this d. And actually, I should do it in a different color. We'll do it in this blue. They put the minus d just to remind you that everything that happens to x is sort of the opposite. And if you see a 4 where k is, it's not actually a stretch, it's a compression 1 over 4. So just remember, whatever you see in front there, you have to do 1 over k. You might say, what if I see a quarter in front of it, and that's the k I see? Well, you just flip it. You flip it, even if it says 3/4, you flip it upside down. And this is actually what's going on. You're multiplying everything by 4 and dividing it by 3, not this. So keep that in mind. And then finally for D, if you see something like that says minus 5, it's not moving everything to the left by 5, it's moving the entire graph by 5. And all of this means, if you know your parent graphs for y is equal to x to the 3 and y is equal to x to the 4 very well, you won't have to worry about anything else. Which is why it's really important to study your parent graphs. Now, as it turns out, I have a transformation graph in here called a transformation tool, which I'll again include. And you can put in any formula you want. So we'll put in the x cubed. And we'll leave all the transformations normal. Now, I've used c here and b, but I could have easily used k. So I'll put in a k and add a k slider. And actually, I'll just make this k. So you can do that if you want, and you can also use the numbers they use. They use D here and they use C here, the letters they want rather. And there you go. Now right now this is no transformation, so at any time you can also pull up a table of values for your x to the 3, and you should know these 5 basic values: minus 2 comma minus 8, minus 1 comma minus 1, 0 comma 0, 1 comma 1, and 2 comma 8. And those are all illustrated there. And I think sometimes you can, if you just click on it, they'll label it for you. And unfortunately, I moved it, but it doesn't matter. You get the idea. Boom. Now let's look at just adding a plus 1 to the c instead of, or plus 3 to the c. Now, according to me, it should go up by 3. And sure enough, the green one is the new graph. It's gone up by 3. And we'll just put it back. Okay. Now, let's look at putting a 2 for a and see what happens. It should be stretched by a factor of 2. Sure enough, and let's stretch it by a factor of 7 to get a good idea. Sure enough, all my y values are multiplied by 7, whatever they used to be. And actually, let's make it a 3. So this y value here is 1 comma 1. If I multiply the y by 3, I should find the same value at 1 comma 3. Since that's the only transformation I did. And sure enough, if you zoom in especially, you'll be able to find it at eventually 1, 3. There it is. And that's what you see is what you get for the y transformations. And the same thing if I put a minus 1 in front of it, it will be multiplied, all my y values will be multiplied by -3. Notice it flipped. It flipped on the x-axis. Everything flipped on the x-axis. Now I'll find 1, -3 down here. If I just, there it is. Oh, I had it for 2 seconds. So it's 1, -3. And all your transformations for y, which are the a and the c, will be exactly as you expect. And actually, I'm going to save it with the k and the c. And the nice thing is you can put any of the formulas in here, and this transformation tool will transform whatever formula you put in here. But again, it helps if you know your parent graph. Same rules apply. Oh, let's do some x transformations. So if I add a 4 here, it won't move to the left by 4, it will move to the right by 4. So the new graph is 4 to the right. So if I add 4 to my x values, I should find the same value here at 5, 1. And sure enough, if I zoom in especially, I will find it at 5, 1. So there we go, 5, 1. And the same if I add a +4, everything slides to the left by 4. So that 1, 1 will now be -3, 1. So if I zoom in on it, I'll discover a -3, 1 if I'm very slow and careful. And you can see that these values are, oh yeah, I should have, instead of put a 4 in there, I should have been adjusting the d value down here. And what's interesting is if you hit play on this, like let's say I'm going to hit play on the d values, it's going to move all the way to the left as it goes positive, and then all the way to the right as it becomes negative d's. And you can do that with all of them. You can hit play on the C, which will raise your graph up as I add values, and bring the graph down. Now remember, C is a y value, so what you see is what you get. And just, you can reset it to 1. Same with the A. If I hit play on the A, it's going to add a stretch to it. Well, this should have been 0 down here, so I'll just put in 0. So it's just stretching it over and over again, and when it hits a minus, it reflects in the x-axis. Okay, and then I'll just set it back to 1. And the same finally with the k values right there. As they increase, you're going to see a compression in the x-axis, and as they go negative, you're going to see a reflection in the y-axis. So I'll give you an example. Here's k is equal to 1. Nothing happens, but here's k is equal to -1. Everything got reflected. It looks like it got reflected in the y-axis, so it's actually easier to raise it a bit first to see what's going on. So I'll raise it up by 3. Now watch what happens to the green when I make k negative. So it's all, and you could still argue it's being reflected in the y-axis. It's probably easier if I end up stretching it to see it better. Let's see if that'll help. Not really. So it's very hard to understand why it looks the same, but with time you'll get that. And the more you fiddle with it, the more you'll understand it. And just try to remember that it will be the same for the x to the 4. And to understand your 5 basic values for the x to the 4 graph. Okay, and I'm just going to get rid of all the stretches and everything. There we go. It's the same now. And you'll want to click on the main points to memorize what they are. And the reason it's 2 to 16 because 2 cubed is 16. Minus 2 cubed is also positive 16. Okay. And you want to learn all the transformations again, but the main thing is that no matter what you do, it's the same transformations. Now, one thing I mentioned before, that is if I raise my new image up by 3, and I'm just going to turn off the purple. If I raise it by 3 and suddenly put a -1 in the a value to reflect it in the x-axis, I'm not actually reflecting in the x-axis. I'm reflecting in that 3 axis that I created by adding 3 to c. So I'm essentially creating a new x-axis. Keep that in mind when you do your reflections. Let's go to what the book teaches. So the book just goes through it again. It gets you used to plotting your basic parent graphs. Then it asks you to actually use a computer, exactly as we did, to adjust the values and see what happens when you adjust them. Then it gives you some examples and says what adjustments are happening here. Very important that you be able to read adjustments both from visual and from words, because that's what they're going to challenge you to. So they're going to ask you to describe in words as well. So let's look at this and see if we can identify all the y transformations by putting a green box around it. And the y transformations are easy to spot. They're going to be outside the bracket, not inside. And then we're going to use purple, and we're going to surround all the x transformation. Now I want you to be very careful here, because in the book it likes doing it like this, and your teacher's going to like doing it like that. That is not correctly transformed. But let's start with the y transformations that are going on. What's going on? Y, we have a stretch by a factor of 8, and then it is translated down the y-axis by 3. And lastly, here's the part that skipped, it is reflected in the x-axis. Now let's look at why the y is not accurate and why teachers love to do this. Whenever you see a half x, and I'll do it in black, whenever you see like a half x plus 1, it's not the way it should be. If that was properly translated, that would have all of that like this, and the cube would be out here, and this would be properly translated. However, the way it's written like this, you actually want the x all alone. So that means you have to factor out that half, and that means dividing each thing by a half. And if I divide each thing by a half to get it outside, I'm going to get a half x plus 2. And you might say, how does 1 become 2? Take 1, and you're factoring out a half, which means you're dividing everything in here by a half. And 1 divided by half is the same as 1 times 2 over 1, which is 2. So that means you have to remember how to divide your fractions. This is the correct translations of what's going on in there. And the book and your teacher will constantly try this trick. So let's describe those translations. It's not compressed by a factor of half, because remember now, that's k value. In this case, this is k. And we have to do 1 over k, which is 1.5. When I do this again, just like this one, we see it's actually stretched by a factor of 2. So you have to be aware of that as well. X will be the reverse. So it's not compressed by half. It is x is stretched by a factor of 2. And then translated 2 to the left on the x-axis, which is plus 2 there. Now, if you're going to turn that into equation, and you can tell right away that this is a cubic, and you know some basic values for your cubic, your 5 basic values are going to be minus 2 comma minus 8. That's all you need to know. Minus 1 comma minus 1. 0 comma 0. 1 comma 1. And 2 comma 8. So if I'm going to now word this into what I should do to my x values, you take all your y values first, let's say. Take y values. You're going to multiply them by 8, by minus 8. Then subtract 3. So that's everything you should do to your y values. And you can also phrase that quicker like this. Multiply by minus 8, subtract 3. However you want to notate it. Then you're going to summarize what you want to do for your x values. Well, all my x values, I'm going to multiply by positive 2, multiply by positive 2, and then subtract 2, not add 2, subtract 2. So that means if you know your parent functions, which you do here, and you take your parent coordinates, and you put the rules, and make sure you get the rules for the right, y's on the right, and x is on the left. That means if I take each of those x values and do that instruction, multiply by minus 2, well, minus 2 divided by minus 2 is, minus 2 multiplied by 2 is minus 4, and when I subtract 2, I get minus 6. And then minus 1 when I multiply by 2 is minus 2, and when I subtract 2, I get minus 4. There's a pattern there. So when I multiply this new one by 2, I get 0, and when I subtract 2, I get minus 2. And then when I take 1 and multiply by 2, I get 2, and when I subtract 2, I get 0. And when finally I take 2 and multiply by 2, I get 4, and when I subtract 2, I get 2. So these are all my new x values. And you want to note it down. Then when I do the same thing for my y values, I have to follow the same rules. So if I multiply minus 8 by minus 8, I get 64. And I have to, minus 8, I get positive 64. And then when I subtract 3, I get 61. When I multiply minus 1 by minus 8, I get positive 8. When I subtract 3, I get 5. When I multiply 0 by minus 8, I get 0, and subtract 3, I get minus 3. When I multiply 1 by minus 8, I get minus 8, and then subtract 3, I get minus 11. Finally, 8 by minus 8 is negative 64, and I subtract 3 is negative 67. Now you can take a graph, and you now have your new x, y coordinates that match up with the same x and y values, and this is how all these points got translated. Now you can take a graph and you can put that in. And now you can just draw it now just by correctly putting those on the same Cartesian graph as these. You'll also see that when you do it with Desmos, so we've got plus 1 and minus 3. Nope, I should have used all my A's and my, A value is going to be minus 8. My K value is going to be a half. My D value is going to be, and I should actually have it as minus in there. Gets confusing. I just kept D as plus so that I would know what's going on. But it's 3, and of course my C is minus 3. Sorry, D is 2. So just to verify. Yeah, now remember that's the unfactored version. It's actually a half x plus 2. And you'll discover that if you take a box value of these, you will discover, especially if you take the same values, you might say, hey, those aren't the translated values, but you got to take minus 6. So it's 62. Oh, I might have done a incorrect by the y. I did the wrong y. So if I took the original y times minus 8, I get minus 64, and then I was subtracting 3. So I've got the wrong C value here. Yeah, it's minus 3. There we go. 61, exactly as I had. And then as if I take the next correct x value of minus 4, I'm going to get a 5. And then 0 becomes 11. And indeed, I'm going to have 0 and 2 is the next one. Oh, it's minus 2 there. I think I got it right, did I? Minus 2 and 0 and 2. So they should be minus 3, minus 11, minus 67. There they are. And sure enough, you'll see them on the graph. So the green one is the translated one, and it's been flipped through the new x-axis, which is here at y is equal to minus 3. So it's been flipped through that part, which is the minus 3 right there. Get used to it. You can also write the formula right in here and it'll do it. But this tool allows you to plug in any values you want. Just remember that D is doing the opposite. I'm going to keep it as plus here as opposed to what they do, which is minus. You can put in whatever you want for the formula, but I like just keeping it plus and remembering that everything does the opposite. All right, let's continue on. So they just keep doing that again. They ask you to describe it, and then they ask you to come up with a formula, and they do it here. See here, they've factored it correctly. So here they first do all the multiplications, and then in the second one here they then do all the subtractions. Just so that you can see it step by step. So they give you another example here, and they just want you to see what happens when it's translated in the x-axis. And then they're doing another translation. This time they're saying I think they're doing exactly what we did. Oh, they're doing it in a weird way. I wouldn't do it this way. I would just leave the half in here. And then here they're doing it again. This is with a quartic. Clearly the y translations are here, so everything's going to be multiplied by 3 and then subtract 48. And the x has no translations except that everything's shifted to the left by 6. So you take all your x values from your parent graph and subtract 6. Take all your y values and you multiply by 3 and then subtract 48. Oh, and they want you to determine the intercepts here. Okay. So they're doing it slightly different. The x-intercepts. So I don't know why they're doing the x-intercepts, but whatever. Here's how you would do that. So x-intercepts are simply when y is equal to 0. So you take your formula and you make it equal to 0. So your first step, just to get x all alone, you kind of reverse bedmass this. So our first step is adding 48 to both sides. So now you get 48 goes to plus 48 on this side. So you get plus 48 is equal to this. All right, that's all it is. And then what's the next step? Well, that stuff happens in the bracket. That's an exponent, so you have to divide by 3 on both sides. And 48 divided by 3 is 16. So you get 16 is equal to this now. And then you ask yourself, how do I get rid of this power to the 4? Well, you have to cube or quarter root 4 root both sides. Now be careful here. Whenever you take a root, you have to see if there's a plus minus. And sure enough, the 4 root of 16 is plus 2, but it's also minus 2. So now we have 2 solutions. And then when you solve for this, you subtract 6 from both sides, and you get x is equal to minus 4. And this one, when you subtract 6, you get minus 8. So those means that when y is 0, these are your 2 x-intercepts, which means your graph, I don't know why no one's answering that telephone, when you graph it, if you wanted to, you could just put the x-intercepts there. Because this is a quartic, it's some sort of W, and it's probably going down and doing a little up. And if I look at it, it's a stretch to the power 4, and it's been lowered by 48, so it's way down. And you can always just put it into your values. So the A is 3, I think it was. There was no K. The only C was minus, was it 48? And the D was non-existent, I think. And we'll just have a look again. plus 6 it was, and minus 48. So D is plus 6. And if you look at it, and you were to get rid of this, and you just kind of get rid of this, and you can see in D there are the y-intercepts, and it's going to form its little bottom right down there at minus 48, because the whole thing got translated downwards by minus 48. So you can see all that happened to it is it was stretched by 3, it was moved to the left by 6, and it was lowered by 48. Which makes sense, because if I lower this by 48, the points that reach the x-axis are way up here, especially if I move them all over here. Anyway, but that's how you would do that if somebody wants to find the x-intercepts. And then it just reminds you what you need to know and checks your understanding. So let's go. So these are always easier if you use a little bit of logic first. Ask yourself, you can eliminate right away. These are cubics and these are quartics, which means these two can only belong to this graph or this graph. That saves you a lot of time. You can also notice that one has a negative in front of it, so that means it's going to be flipped on the x-axis. Well, this one's starting normal and ending normal, so the only one that's flipped on the x-axis is this one. So that must be B, and that must be A. But there's a couple other things you can figure out. You can automatically say, well, it's been moved, this A1 has been moved to the right by 3 and raised by 1, which is clearly this one. It's up by 1. You can also say this one down here has been moved to the left by 1 and lowered by 1, which is clearly this one. It's moved to the left and it's lowered. So those are already automatic indications right away that allow you to match up with the right thing. This one has been moved to the right by 4 and down by 4, which is almost or down by 3, which is almost automatically that one. But the other telltale sign is this one's negative, which means we're dealing with a downward facing quartic. And this one's positive, which means we're dealing with an upward facing quartic. All these things can be used to justify your logic about where they are. Especially this part of it, right there, will always be the C value. It will always be the C value. So wherever it's now rotated around should match these numbers right here. See? 4 minus 3 minus 1 plus 1. Those are always easy to do. State the parent function. Number 2 and number 3, state the parent function. That must be transformed to create the graph in the following things, then describe the transformation that must be applied to the parent graph. Well, this is a quartic, this is a line, this is a cubic, this is a quartic, this, when I expand it, is a parabola, and this is a cubic. Just keep in mind that that's not properly translated. This you would have to put in proper terms to see the translation. It's just the same thing squared. That's not properly translated, and everything else is fine. So when I'm looking at this, the parent graph here is a quartic, and the transformations that are going on is this. There's no translation to the x, so my y values are stretched, because 5 over 4 is bigger than 1, by a factor of 5 over 4, then vertically translated up by 3. I should have said vertically before. That's it. That's all that's happening in this one. Next one. So when it's written like this without brackets, you know that this one is a y and this one's a y. So the only thing that's happened here is we have a line with a slope of 3 that is stretched vertically by 3 and translated vertically, sorry about spelling, downwards by 4. And that's all that's happening to that one. And you just keep going through those, and what they want you to do is get used to expressing it in words. Okay, so this is not correctly factored. I have to get a 3 out and keep it within its cubic bracket. And when I divide them both by 3 to get the 3 out, I end up with this in brackets. Y is equal, open brackets, 3, open brackets, x plus 4 over 3, all to the power of 3 minus 7. So this is what I end up with. And now I can see that this is a cubic, and here are the y transformations. There are none except for translated vertically down by 7. Then it's got a horizontal, not a stretch, but a compression by a factor of 1/3, and horizontally translated to the left by 4/3. So that's essentially, it's going to the left by 4/3. And there you go. So if you have the parent graph, that's what you would do to each of the numbers. So this is a cubic, and you'll notice again that, oh, I just did that one, sorry. So this is a quartic, and there's not much going on with it, so it's pretty easy, except for the minus in front. Now that's outside the bracket, so that's a vertical. That's a reflection in the x-axis because it's affecting the y value, which means every y value gets multiplied by, to carry it out, you multiply y values by -1. And then it's translated to the left, sorry about the spelling, horizontally translated to the left by 8, which means you take all your x values and you subtract 8. Now, sorry if I didn't write the rules to what you do to the values to the parent graph, but that'll help you as well. Okay, so I'm going to go to this one. All these are just more about how to interpret data properly. Now I'm going to just rewrite this in an easier form. I'm going to just rewrite this as squared. And we can see it a lot clearer this way. And we can just leave the -4.8 as a y translation. So we can first say y, it is stretched by a factor of 4.8, which means and reflected in x-axis, which just simply means you take all your y values and multiply them by -4.8 to get the new y values. Then the x translation is it's horizontally translated, sorry about the spelling, 3 to the right because it's -3. So take x values and add 3. And you'll get all your new translations. Now, notice this is just a parabola. It's been flipped. It'll be downward facing, stretched by 4.8, and everything will be moved to the right by 3. And again, if in doubt, you can always get practice with Desmos. Now this one is getting tricky because notice it's not correctly factored. Okay, so that means I have to divide everything inside that bracket by 1/5. And what is 7 over 1 essentially, divided by 1 over 5? It's the same as 7 times 5 over 1, which is 35, which means inside that bracket, I can rewrite this whole thing as y is equal to, there's a y stretch, 1/5 comes out, and I get x plus 35 when I divide that 7 by 1/5. And I can't forget to put the little cube up above, which means I have a vertical stretch by factor of 2 and a vertical translation down by 4, which means you multiply all your y values by 2 and subtract 4. Then x, I have a horizontal, not a compression, but a stretch by a factor of 5, because it's the flip of 1 over 5, and a horizontal translation left 35, which means you multiply all your x values by 5 and then subtract 35. And you'll get all your new values. Now, obviously, this is a cubic. So if you know your parent graph, you'll be able to come up with 5 new points, connect them, and then draw it the way you know a cubic should look. And just keep in mind of the horizontal reflections. So this is very similar. Describe the transformations that are applied to the parent graph and create each of the following graphs. Then write the equation of the transformed. Okay, so this is a little tricky. So they're telling you the parent graph. And the trickiness is that you have to come up with its A, its B, and you know what? This is not as easy as it looks. The only benefit is they tell you right here the new vertex. Well, not the vertex, but the new origin. So it used to be 0, 0 for all the parent graphs. So that means I've been moved to the left by 3, and moved down by 4. So right away, I can say with confidence that there is a C out here of minus 4, because I can see my new axis right there. So minus 4 is going to be out, and then I can also say in brackets it's going to be x plus 3. And that helps a lot. That helps a lot. So that means I can rewrite it already like this, as long as you can spot the new origin. I don't know what my A is going to be. Does it look reflected, by the way, an x cubed? No, it looks normal. So my A is going to be positive. I know it's going to be x plus 3, because it moved 3 to the left. And I know it's going to be minus 4. But in brackets here, I don't know if what the k value is that affects 3. I just know it's been moved down by 4. So I know half my y values and half my x values, and just keep in mind it's to the exponent of 3. So then, if I have to keep up my A, I would then look at my next values right over, and I can see it's 1 to the right and 1 up, which to me means the y value, and these ones next over are only 1. Since I know it normally goes 0 to 0, and now it's going 1 down and 1 down and plus 1 up, plus 1 up, I would suspect there's no stretch and no A. And the secret here would be to take a shot and just rewrite your A, and just rewrite it as this, and see if you plug in a couple values that they give you. For instance, if I take minus 1 and put it in this equation, will I get 4? So I'm going to take minus 1. I'm going to add 3, it's plus 2. 2 cubed is 8. When I subtract 4, I indeed get 4 when x is minus 1. So that one works. If I take some other ones like minus 2 here, if I plug it into the equation, minus 2 plus 3 is 1. Cubed is 1 minus 4. I get the equation minus 2 minus 3, which is indeed that number. If I take minus 3 in here, and I add 3, I get 0. Minus cube doesn't matter, it's 0. And then subtract 4, I indeed get this number. So I can see already that all the numbers are working out fine. And I realized it wasn't stretched because the very next units, how did I realize it wasn't stretched? The very next coordinates to the left and right were the same as the normal coordinates. They were just 1 over and 1 up, and 1 down and 1 left, which is how the 0, 0 of the parent goes to 1, 1 and negative 1, negative 1. So I could see they weren't expanded at all. They weren't stretched. This one's going to be a little harder, except, and I'm going to go straight to C instead of A. But I can see it's a cubic, and they do indeed give me the origin. So I can see that the origin has indeed been moved 1 to the right and 2 down. And sure enough, there's the new x-axis. So right away I can say it's going to have a minus 2, and in brackets it's going to have an x plus 1. So if I were to rewrite it, I don't know what the A is. I do know the a is positive because this is facing upwards. And I'm going to get x minus 1 to move it to the right. And the whole thing's going to be minus 2. But the big question is, will there be a k? What will there be a k? What will it be? And also remember, it's all to the cubed. Now, it gets a little bit tricky to actually figure these out unless you start just plugging in the exact numbers. You can take the 2 here, and you can take the minus 1 here, and you can try to solve k and a. The problem is you're missing 2 values, so you're never going to quite, you'll need at least 2 to figure it out. But let's give that a shot. Wherever I see y, I'm going to take this value here, and I'm going to plug it into the equation I have so far. So I'm going to take, I know my y is 2. I don't know my a. I don't know my k, but I do know my x is minus 1, and it's going to be subtracting 1, and it's going to be to the power of 4. So I'll just have to remember that, and I'm going to be subtracting 2. And I take it as far as I can. So minus 1 is minus 2, and to the power of 4, it becomes positive. So I know it's going to be 2 to the power of 4, which is 4, 8, 16, positive 16. So I know I'm talking about 16 AK, 16 times my a and my k, which I'll just leave in front, and then subtract 2. Well, if I get that 2 to the other side, that becomes 4. So I know that I now have a temporary formula that says 16 times my a and my k is going to be equal to 4. If I divide by 16, I know my ak is going to be 4 over 16. What's 4 over 16? It's 1 over 4. So I know a times k is 1 over 4. So that's good so far. Now you might say, oh my god, that's complicated. Yeah, it's okay. Don't sweat it. It's all experimental. Then I'm going to take my other value, and I'm going to do the same thing that I did with this one. Wherever I see y, I'm going to put in a 2, and I'm going to leave my a. Whenever you're missing 2 values, you need 2 separate equations. I'm going to leave my k, and what's my new x? 2 minus 1. What's 2 minus 1? It's 1. 1 to the power of 4. What's 1 to the power of 4? It's just 1. So I get a times k minus 2 is equal to 2. So ak is equal to 4 in this case. Now I have 2 equations. I can say now my k is the same as, divide both sides by a. My k is going to be equal to 4 over a. Now that I have an equation here for k, I can replace this value of k into this value of k. And so I get a times, oh no, it won't work because all I'm doing is eliminating it. Yeah, that won't work. So I would need to sort of understand what those, if those values are indeed the next values. I think that makes sense. So that is a way to solve it, but the problem is these are mirrored on either side. So if I look at what the next value should be, the next values on my normal cubic are 0, 0, 1, 1, negative 1, 1. And if I see this, this has gone 2 over. So I'm going to guess that it's factored of 2 because it's gone 2 over stretch, which means my k is probably 1 over 2. And that's because my 1 went to this minus 1. So I'm going to try a half as k. That might make sense. Then I can see my 3 also did the same thing. It went over by 2. So 1 over 2 is probably my k. I can see my y's went from minus 2 to 2, whereas it normally only goes 1, which means my a is probably 4 because it went 4 times farther than it normally does. It normally goes up by 1, and here it's gone up by 4. So that's the way to see it. It's gone, the x values have gone a factor of 2 this way, and a factor of 4 that way in the y values. And yeah, that's a lot of guesswork, and I think there's probably an algebraic way to do it. But I will now say that it will be y is equal to 4. My k will not be 2, it'll be a half, because that's how I'd have to express k. And then my x will be x minus 1 to move it 1 to the right. Then it's going to be all to the power of 4. And then, as I mentioned before, it's going to be lowered by 4. Then we test it out. So we take a couple of these numbers, 3 comma 2, and we put it in for x and y. So we're going to go 2 is equal to 4 times a half. What's the x value? 3. So 3 minus 1 is 2. 2 to the, and then all of that's got to be multiplied to the power of 4. And then subtract 4. So when I do 1 half times 2 here, I get 1. 1 to the power of 4 is 1. 4 times 4 is 0. Oh, let's see. I'm not getting the right value here. Oh, yeah, I should have just been plugging. Sorry, I should have just been plugging in my x value. So if I take y, I'm going to figure out if it's 4 times a half. And my x value is 3. I did 2 by mistake. 2. No, I didn't. To the power of 4 minus 4. I forgot to multiply it by 4, though. So I get 1. No, I didn't forget. So I'm not getting that value, which means I did not do the correct stretch. I think I got the 4 right, but I believe it might have been 2, which is interesting. I would have thought it did the opposite. 2. Still think I'm right. Oh, I know what I did. Look at that. Stupid. It's not minus 4. It's minus 2. Dumb. Sorry about that. So if I do it again, I had a feeling the stretches were right. If I do it again, I get claiming it's a stretch of 4. Now for x, I'm putting in that 3. 3 minus 1 is 2. Times a half is 1. 1 to the power of 4 is 1 times 4. And then subtract 2. Indeed, my y is 2. Exactly as it should be. Then when I do it with the other x value, when I do it with this x value instead, and I put in where I see x, and I get a half, and my x now is minus 1, which is minus 2. What's a half times minus 2? It's minus 1. Minus 1 to the power of 4 is positive 1, times 4 is 4, and then I subtract 2, I indeed get 2 again, just as I should. So to figure out what the stretches were, I had to assume that these are the first 3 points in the parent graph. And it's, it gets a little mentally tricky doing it that way. I'm sure there's a more algebraic way to do it. So clearly this is a quartic, and clearly it's facing down, which means the a in front is going to be negative. You can also see the new, I guess, vertex in this case, which means I know I'm dealing with y is equal to a, and I know a is going to be negative, and I know it's x plus 4 because it's moved 4 to the left. It's all going to be to the power 4, and then plus 5. And then the question is, how much stretch did it occur? Well, normally they're 1 apart, right? But minus 4 to minus 3 is still minus 1, so the x didn't get stretched at all. And the y is going up by 2 on both sides. It's going down by 2, which means this a is probably minus 2. The x's only went down by 1, so they're just 1 apart. So right away, and again, I'm pretty sure there's an algebraic way to do it. I'm just using logic. This is my assumption. X didn't get stretched at all. It's all to a power 4, and it's all plus 5. If I take any one of my points, so I'm going to take minus 3 as my x value, I should get 3. So I'm going to do y is equal to minus 2. What's my x value? Minus 3 plus 4 is 1. 1 to the power of 4 is 1. 1 times minus 2 is minus 2. Plus 5. Minus 2 plus 5 is indeed 3. So I got it right for that one. Then I'm going to do it for the other point, which is minus 5, comma, and I should get 3. So I do y is equal to minus 2. Minus 5 plus 4 is minus 1. Minus 1 to the power of 4 is 1. Times minus 2 is 2. Minus 2 plus 5, and again I get 3. So right away I can see that this is probably the right equation. The stretches are the tough part. Now I'm pretty sure if I had a couple other clean points, I can find the a and k by using two separate equations and substituting one for the other. I believe it doesn't work in this case because they're all along the same y value. But if you had another point down here, let's say, it should work. And actually, I might have done a calculation error because of that +4 I was using. So this next one, I'm going to see if I can do it. So I think we just did that one. So let's see if I can do it algebraically. This one, we can see the new origin is there. We're dealing with a cubic. It has got a negative in front of it because it's flipped in the opposite direction. So I know I'm going to have y, and I know my a is going to end up being negative, but I'll just put a for now. I can see that my x has moved 3 to the right, and my y has been lowered by 4. Let's see if I can do it algebraically. So I'm trying to figure out a k. Now I believe I could do it with just an a. I believe I can do it with just an a. And let's just try taking a couple of values of y. So I'm going to take -6. Should be able to do it with 3 too, but we'll see if it works algebraically. And I get a, k, and my x is 4, so I get 1 cubed. So I get k cubed. Oh, that's what I was doing wrong. The k has to be cubed. So k to the power of q. And all of it -4. When I move to the 4 to the other side, I get -2 is equal to that. Then when I divide it by a, actually I'm going to just get a alone. So it's -2 divided by k to the power of 3. Now I believe if I just ignore the k and solve for a, that it makes it easier. And I believe that's still works. And technically I should probably do that. So I have a is equal to this. Then if I take the other point, -2 is equal to a, k, and 2 minus 1 is -1. So this time it's going to be -k cubed, which is the same as -1 times k cubed. And all -4, and the -4 goes to the other side, and I think this is the same problem. It becomes this, +2. And so if my a is equal to what I have up above, yeah, see, it doesn't solve it. So I think what I have to do is just leave k and maybe solve it like that. Or do the logic I was doing. I think I have to skip k and say if I have any one of these values, (1 cubed -4), and I get -2 is equal to a. And I believe that will work. Now let's just see if that's true, and maybe they told us in the beginning. So if I look at my x values, they are indeed only going up by 1 and 1. And if I look at my y values, they are indeed going up by 2 when they normally go up by 1. And since it's inverted, -2 makes sense. Now I think that only worked because my x values were not compressed. And I believe you can probably get away with just doing a here and come up with a formula for the graph, but I don't believe that technically that's the right way to do it when there are x compressions. It could be that there's a way of putting some of these numbers in the graph because, I mean, every vertical stretch can have a horizontal stretch. Any vertical stretch can have a horizontal compression that creates the same graph. Confusing, I know. Algebraically, you might want to ask your teacher if he has a sound algebraic method. I'm just doing it visually. Describe the transformations to create the following. Okay, just remember that they will always, the one thing they're always going to be tricky about is the actual x translations in the middle. Now, as it turns out, this one has everything in it, so the y translations is stretch by factor of 12 and translated down by 7. So that means you take all your y values, multiply by 12, and subtract 7. Your x has only one translation, the -9, so that means all your x values are translated right by 9, which means take all your x values and add 9. And if you do that with 3 of them, you can come up with a new formula. So that's that one. Oh, this one they've actually translated the x values correctly. And you can see that there's only one y. Y has been translated up by 3. And x values, x has been stretched by a factor of 8/7, and then translated left by 1. So you take all your x values, you multiply it by 8/7, which is the reciprocal of 7/8, and then subtract 1. And you'll get all your new x values and all your new y values. Oh, the y translation here is simply subtract y values, add 3. And there you go. You can see how easy the y values are. Okay, and this is a cubic. We can see a translation in a reflection in the x-axis. So y stretch by 2, reflection in x-axis, and translated down by 8, which means take y values, multiplied by -2, then subtract 8. And the x translations, x translation 6 to the right, which just means take your x values and add 6 to them. Now this one looks trickier than it is. And just keep in mind that that is the same as x plus 9 cubed. And you can instantly see that there's only one x translation. And the x values are translated left by 9, which means take all your x values and subtract 9. And they're very nice, this one. They've done all the x translations properly for us. And they're just making it confusing. So how you describe it, the y stretch by 2, reflection in x-axis, that's the negative, and translated down vertically by 5. Sorry if I skipped the vertical before. Which means take your y values, multiply by -2, and then subtract 5 from them. And then for your x values, they have been not stretched, but they've been compressed by a factor of 1/3. Then they've been reflected in the y-axis, that's the negative. Then translated horizontally right by 4, which means take all your x values and multiply by -1/3, then add 4. That's all there is to it. And finally, the last one is a cubic. Sorry if I haven't named the graphs. And it's very, very straightforward. It is an x stretch by a factor of 4/3, 4/3, and translated horizontally to the right by 10, which means multiply all x values from your parent graph by 4/3, then add 10 to them. The y values just stay the same. And you'll be able to plot that graph. That was your practice. Let's get to 5. And some of these, I'm gonna be rusty on them. Translations aren't my. I'm okay at them, but. Okay, so they want you to figure out the H, figure out the K, and figure out the A. And I'll tell you right away, the K is the easiest thing to figure out. Notice they're mixing up the values here. That should be C. So, because it's a parabola, it's because it's a parabola. So you're going to find your K and your negative H at the vertex, because it's a parabola. So 0, 12, which means that there's no H, and the K is -12. So right away I can say, okay, I'm going to rewrite that as y is equal to and I'm only doing a right now. Y is equal to a, and I don't know my a, but I do know the x is going to be squared, and it didn't move anywhere. It's still at 0. And the k is minus 11. And that's the nice thing about parabolas. And then to figure out any of the a, I just need any other point. And it gives me 1 comma minus 3, so I'm going to use that. And my a, and what's 1 squared? It's just 1 minus 11, which means a, or if I move that 11 to the other side, 8 is equal to a, which means I can just put 8 in here. And if I'm not sure that I got it right, I can take one of these points. Let's say I can take minus 1 and see if I get minus 3 out of it. So I take minus 1, I square it, 1 times 8, yep, subtract 11, minus 3. Yep, I got minus 3. So that's the formula, and it's easier with parabolas. Now I believe that's 1.25 there. So that means my interesting 1.25. Okay, because it starts as 0, 0, it can only be this. So my x is still the same. I don't know my a. It's facing downward, so at the end I'm going to have a minus in front of that a. But I have x, and the whole thing squared, and it hasn't been translated left or right. And then I'm going to add 1.25. And then when I take any point, I'll take the 5 comma minus 5 and put it in. I get this. What's 5 squared? 25 plus 1.25. You can see that the a is going to be a bit messed up. Then when I move to the 1.25 to the other side, I get minus 1.625 is equal to 25a. And it's quite possible that the reason this is all messed up is because there is a stretch at the x as well. And I discover my a is equal to negative 6.25 over 25, which is true. But I can also see that the value of x went up by 5 at the next point. It all depends if that's the valid point or not. 1 comma 1. So more likely it's something like this, and it went up by 6.25. It's probably negative 6.25, and it's probably a factor of 5 for the x, and it's probably x, all of that squared, and then plus 1.25. Now you could test that out and see if I plug in 5, will I get minus 5? Might be a little bit tricky. I might have it wrong. 5, and 5 times 5 is 25 squared. Yeah, definitely not going to work. So you should probably just stick with the original a I had, which is that. Now, personally, I don't think that's accurate, and I think it will work out. And you can always test it out with the other one. So you get this is minus 6.25 over 25. What's minus 5 squared times 25? So clearly the 25s will cancel out. And when I add 1.25 to it, I get y is equal to negative 5, which is indeed this point over here. Personally, I think this is probably a combination of the two. And it's, like I said, it's, oh, I know what it actually should be. It's actually this. I just put the 25 in there incorrectly. It should be 1 over 5 instead of 5. And that should be squared and plus 1.25. And that's more accurate because I can see that the x's are going up by a factor of 5, which would be 1 over 5. And if I sub in 5 in there, what's 1/5 times 5? It's 1. What's 1 squared? It's this, and I get the same thing. So actually, this is probably what is actually going on. But they have not given us a k value here. They've only asked us to figure it out as if it's a. So this is probably actually what's going on. But this is the a value we're going to put. Either one will come up with the same graph. Interesting. So it's a good example of when stretches of y can also be expressed as compressions of x. And all I did was take that 125, find the square root, and put it inside the bracket. And 1 over 5 creates the effect of a multiplier of 25. It's very hard to see what I did, but you probably will get good at it with practice. Since they only ask for A, only do what they ask for. So here's X. Sorry, here's number 6. So they're asking us just to use words. So it's saying x cubed has undergone the following transformations. If x cubed passes through these 3 points, list the coordinates of these transformed points on the new curve. So they're doing several compressions. So let's just write down what it means. Vertically compressed by half, so that means multiply your x values by half, your y values by half. That's vertical. And then they just say, they jump straight to horizontal. There's no more vertical. And they say it's horizontally compressed by a factor of fifth. So that means multiply, and you just do it exactly. And I'll look this up to make sure. Since it's compressed, I'm going to multiply by a factor. Multiply your x values by 5. Actually, I think it's going to be by a fifth. And translate it 6 units to the left. And then subtract 6. So let's see if we get that. So the minus 1, when I multiply, we're going to take the following values that they give us. Minus 1 comma minus 1, 0 comma 0, and 2 comma 8. So if I take those values and I take this one and I multiply by a half for the y values, I don't know what my x is going to be, but my y value is going to be negative a half. If I multiply my x values by a fifth, I'm going to get negative 1/5, and then when I subtract 6, I get negative 6 and 1/5. We'll see if that's right. When I multiply 0, I get 0, but then when I subtract 6, I get 6, and then for y, I just get 0. And then for the 2, when I multiply by a fifth, I get 2 over 5. When I subtract by 6, 2 over 5 minus 6 is minus 5 3/5. And then my y value, which is 8, when I multiply by half, becomes 4. Now I'm going to just jump straight to the answers for number 6 to see if I got the what they were looking for. So if we look at 6, we can see these are the translated points right here. And the reason I kept the compression for x the same is because they've already translated it in words for me. So sure enough, there's negative 6 over 5 and negative a half. Here's negative 6 and 0. And here's negative 5 3/5 and a quarter. In case you're wondering how I came up with a negative 5 and 3/5, 2/5 minus 6 is the same as minus 30 over 5, which is minus 28 over 5, which is the same as negative 5 and 3/5. I can also just say, well, 2/5 minus 6 is the same as minus 5, and what's left over from a whole of 2/5? 3/5. You'll figure that out with time. So because they've written the translations already, you don't have to convert the k's and the y's. You just have to write out in words what to do with your x and your y values. So let's look at the next one. So they reflect in the y-axis, which means take your x values and multiply by negative 1. Then they say stretch by a factor of 2, so you multiply by negative 2. And then they vertically up by 1. So take your y values and add, vertically up by 3. So if I do that with minus 1 comma minus 1, and I multiply the x values by minus 2, I get 2. And my y values, I take your y values, and I think they said add 3, right? Yeah, add 3. My y values become 2, so that first one becomes 2. 0, 0 becomes 0 when I multiply by minus 2, and when I add 3, 3. And 2 comma 8 becomes, when I multiply by minus 2, minus 4, and when I add 3, it becomes 11. So these should be my new values for 6b. And again, if I go to the answers, they're right here. And that's exactly what I got. Okay. So because they've already described the horizontal stretch properly, you don't have to do the whole opposite thing. It's only when you see it in equation that you have to do it in opposite. Once they write it in words, they've done the opposite already. So then here at C, reflected in the x-axis, so that means my y values are multiplied by -1. And stretched vertically by a factor of 3, so not by -1, but -3. Then horizontals translated to the right and vertically translated. Oh, they added a vertical translation afterwards. So they added a vertical translation of a half down, so subtract a half. And then your x values are vertically stretched by are horizontally stretched. Horizontally translated to the right by 3. So x values you just by 4, sorry. So x values just add 4. So then you take all those values and -1, -1 becomes add 4 to it, 3, and multiplied by -3 becomes +3, and subtract 3 becomes 2.5 or 2.5. 0, 0 becomes 4, and then multiplied by -3, 0, subtract a half, -1/2. And then 2, 8 becomes add 4 becomes 6, and then multiplied by -3, -24, and subtract half, so it's -24 and a half. And you'll discover that's what you need to, that's what your answers will be. And then just the next ones. You can see they're doing it over and over again. So vertically compressed by a factor of 1/10, so y values multiply them by 1/10. Horizontally stretched by a factor of 7, so x values multiply by 7. And then it says translated 2 units down vertically, so then you have to subtract 2 from your y values. Then subtract 2. So that means if I take those values of -1, -1, that becomes, when I multiply by a tenth, it's -1/10. Subtract 2, it's -2 and 1/10. Now that's the y value. The x value, I simply multiply by 7. So I get -7, -2 and a tenth. 0, 0. The x value, when I multiply, stays 0, and then subtract 2. The y value stays 0, or the x value stays 0. The y value multiplied by 10 stays 0, and then subtract 2 becomes that. And then 2, 8, when I multiply the x by 7, I get 14. And when I multiply the y value by 10th, I get 8/10. And then when I subtract 2, I get -1 and 2/10, which is the same as 1/5. And you'll discover that's what that is. Then when I do E, you'll see that it's reflected in the y-axis, which means my x values have been multiplied by -1. And reflected in the x-axis. So that means multiply your x values by -1 because it's reflected in the y-axis. Then multiply your your y values by -1 because it's multiplied in the x-axis. Then it says vertically translated 9/10 up. So that's vertical translation. So then add 9/10 to your y value. So at -1, -1, that becomes +1. +1, and then add 9/10, 1 and 9/10. At 0, 0, it becomes 0. And then multiply this by -1, 0, and then add 9/10. And then your 2, 8, when I multiply by -1, becomes -2. And then it becomes -8. And then when I add 9/10, it becomes -7 and 1/10. Those things are kind of hard to figure out. Practice your fractions. And then finally a horizontal stretch by a factor of 3, or sorry, factor of 7. So that means, and a horizontal translated 4 to the left, so they're doing x values when they say horizontal. So you multiply all your x values by 7, and then you subtract 4. And then vertically translated 2 down, so take all your y values and subtract 2, which means -1, -1, the x value I will multiply by 7. So minus 7, and then subtract 4, minus 11. And then just subtract 2 for your y values. 0, 0. You multiply by 7, you get 0, and subtract 4, you get minus 4. Then y values, subtract 4, so you get minus 2. Or, yeah, subtract 2, rather. And then finally 2, 8. When you multiply by 7, you get 14. Subtract 4 is 10. And 8 times, you just subtract 2, becomes 6. So these are your new y values. And you can always go to the back of the book at 625 and discover all of these values right there. Very good to practice these things, though. Okay, number 7 and 8. I might have to stop early. The graph shown is the result of a transformation of a cubic. Of y to the 4. Determine the equation of this transformation. So this is going to be a little bit trickier because I don't know if they've given us the exact values. You can see that this is origin, and it's been moved 1 to the right and 3 up. So right away I can say at least y, it's also been flipped downwards, so I know a is going to be negative. And I can just say x plus minus 1 to the power, all to the power 4, and then add 3. Now I can see the 1, if that's the very next point, the 1 went to the 5. And normally it would go up by 1, but it went up by 4. So I can almost automatically say that the multiplier in front of the x is going to be 1/4. And then I can say the multiplier of the y's, it went from 3 to 61. So that's a 58 multiplier. So I can almost automatically say that's 58. If I'm going to put this into Desmos, you know, I should be able to see it. Let's just take a chance and do a new Desmos and take y is equal to minus 58, and then for x I can set that it's going to be a multiplier of what? 1/4, and then it's going to be x minus 1, and it's all going to be to the power of 4. And then I said it moved 3 to the right, right? Now I'm going to make a table, and I'm going to find when it is minus 1. When it is 1. So I can see that that's 3. Then I'm going to find, they told me minus 3, I should get minus 61. No, I don't. And 3, I should get 61. Is it 3? 5. I should get 61. And I don't. So I didn't quite do the multipliers right. So if I look at my y, it's going from 3 to 61. So normally it would go from 0 to 1. And it's going from essentially 3 to 61, which, oh, I know what I did. That's not minus 61 down. 61 plus 4, this is minus 64. Let's see if that does it. And sure enough, let's ignore these values. Sure enough, I get exactly the points they said. Now you might say, how do you figure that out? And that's because normally it goes from 0, 0 to 1, 1. And that means there's no stretch. The next point is 1. Because it went from 1x value here to 5x value here, right? So it's going that way. And it didn't increase by 1, it increased by 4. That means I have a stretch of 4 on my x value. Well, stretch is not by 4, it's written as 1/4. So that's how I came up with 1/4. Then when I looked at my y value, it went from 3 all the way down to negative 61, which is a distance of 64, which means it has a stretch of 64. And because it's facing downwards, I put a negative. Now, all of that is visual and guesswork. And you might say, I'm not going to be able to necessarily prove that. And you'd be right. So one thing you can do, though, is just you know that the horizontal translations are this. You can forget your k, because it's too hard to do, and you can just figure out a suitable a value. And what's interesting is your suitable a value will still work. It just won't be exact. It will give you the correct answer, but it won't be perfect. And then you just put in one value for y that you have, and you put in your value for x, which is 5 minus 1. What's 5 minus 1? It's 4. What's 4 to the power of 4? 16. 32, 64. It's 128. Okay, and then all adding 3. Now we do know the 3 is right and the translation of 1 is right, because that's evident from the vertex. When I move the 3 to the other side, I get minus 64 is equal to a times 128. Therefore, a is equal to minus a half. And you might say, well, that's not what you found, Peter. But guess what? If I do y is equal to negative a half times x minus 1, and then it was plus 3. Oh, sorry, to the power of 4. Plus 3. Oh, maybe I did a small calculation error. We'll have to try it again. But you should get the same value. Let's see if I got it right. So I'll try it again with the calculation, because I probably got the calculation wrong. We're just going to keep this as the base equation. We're not going to put in a k. We're just going to solve for a. So let's try that again. So we got minus 61 is equal to a. What's my x value? It's 5 minus 1. What's 5 minus 1? 4. What's 4 to the power 4? So I'm just going to make sure. I'm pretty sure it's 128, though. 1, 2, 3. Oh, 256. That's where I screwed up. So it's 256. My bad. Plus 3. 56a plus 3. So I still get 64 is equal to 256a. And then a is equal to a quarter, not a half. And it's negative a quarter, because that's negative here. So I just did a calculation error. So if I put in a negative quarter here, look at that. It's the same graph. And you might say, well, how come? And that's because I've just accounted for everything with a vertical compression. Now you could, it would be very hard to come up with that 64. And your teacher might be able to tell you a more sufficient way. I don't think the book's going to tell us a good way to do it. We can try looking. Now the book is just going to, oh, look at that. The book just gave a y compression. Even though my intuitive thing is probably more accurate. All they did was solve for a, which made it a lot easier. Now guess what? You can also come up with this equation. Instead of putting this minus a quarter here for a, you can just put that quarter into here as a 4, because it's the reverse of what you want. And because you know it's going to be cubed, it would be the cube root of 4 would do it, I think. That's pretty confusing for you, I know, but it's as if the 4 got cubed and then came out, and it came out as a quarter. So when you find the cube root of a quarter, I don't want to make it too hard. So you have a quarter, and you find the cube root of it. Where's the second function? No, somewhere. There we go. Right there. So I find the 4. Yeah, I don't know if that'll do it, though. 0.7. Yeah, it does. So that's even weirder to think of. I essentially put the quarter into the x compression or stretch as 0.7. Look at your book. There's an example in your book of how to that. But anyway, you can see that the book is just focusing on the A compression, even though technically that's not what's going on here. And it's a good example of being able to come up with different equations that have the same graph. So he has reflected a function x to the 3. He's vertically compressed it by 2/3, horizontally translated it, vertically translated it, and he's got 3 points. And they want to find the original coordinates of those points. Now that's interesting because they're working backwards. So let's write down how he did it. Let's focus on the x stuff first. Vertically compressed by a factor of 2. So he took x values and he multiplied by 2/3. Then he horizontally translated 13 units to the right. So then he added 13. Then he vertically translated it 3 down, but he also had a vertically compression. So actually he has no horizontal compression. He just added 13. Vertically, he took the y values and he multiplied by 2/3, then subtracted 13. And he ended up with these points. So he had mysterious x1, y1, and when he added 13 to x and multiplied y by 2/3, and subtract 13, he ended up with 11 and negative 23 thirds. So what you have to do is reverse that process. So since he does it in order, he multiplied by 2/3 and then he subtracted 13. We have to add 13. And you do it with each of the coordinates he has. So let's do it with, he started with an x1 and y1. He added 13 to x values. And then he multiplied y values by 2/3, and then he subtracted 13, and he ended up with 13 and mega 13. Now this one would be easier to do, because if I subtracted 13 and ended up with minus 13, that means I was at 0. And what do? I don't multiply by 2/3, I divide by 3/2, but I still end up with 0. For the x value, when I added 13 and came up with 13, it's clear that the original point here is 0. So right there, I know in this case, the easy one is 0, 0. And then the last one, he came up with, he took an x value and a y value, and he added 13 to x values, and he ended up with 15. So if he added 13 to the x value, it's obviously 2, right? Up here, if he added 13 to the x values and he ended up with 11, it's obviously that x is minus 2. So you can see some of these are very easy to figure out. But in this case, he added the y values, so we figured out that. But for the y value down here, he ended up with minus 55/3 after adding or subtracting 13. So 55 over 3, it helps to figure that out. So you just take 55 and divide it by 3, and it'll tell you the leftover. So it's 18 1/3. So that's 18 minus 18 1/3. So if I got to 18 1/3 and by subtracting 13, that means I started at 5 1/3. And since I multiplied that by 2/3, I now must divide it by 2/3 or multiply it by 3/2. And that's how you do it. So if I go back, I might as well take his original number. He had minus 23, and he subtracted 13. Oh yeah, and he ended up with minus 5 1/3. Putting that back into fractions, that's minus 16 1/3. If he multiplied by that 2/3, I can now divide by 2/3 or multiply by 3/2, which is the same as minus 48 over 6. 48 over 6 can both be divided as minus 8, I believe. 48 divided by 6. All I did was reverse the mathematical order. So I'm claiming it's minus 8. Let's see if that's true. If I take minus 8 and multiply it by 2/3, and then subtract 11, or sorry, subtract 13, will I end up at 18 and a third? Negative 18 and a third. Yes, I do. So you can see that I started with minus 8. In this one, I ended up with negative 55 and a third. Oh, that was the second one, wasn't it? So it's negative 8 here. In this one up here, I ended up with negative 23 and a third, which is 7 and 2/3. Since I subtracted 13 to get there, that means I started at positive, this is a tough one, so 6, 5 and a third. And then and that's the same as minus, positive 5 and a third, and that's the same as 16 thirds. And since I multiplied it by 2/3 to get there, I multiply it by 3 over 2 now, and I end up with 48 over 6, and that's 8, and I believe that's positive 8. So I believe these are the values that I should have: minus 2 comma 8, 0 comma 0, and 2 comma minus 2. I might have made some calculation errors, but it's essentially moving backwards from the process. So let's see what the answers were. Got it. You might say, how did I do that? Well, since I know the mathematical steps that got me to the final value, I just reverse those mathematical steps, and instead of subtracting 13, I add 13. Instead of multiplying by 2/3, I divide by 2/3, which is the same as multiplying by 3 over 2. And instead of adding 13, I subtract 13 from all my x values. I will end up at my original values. And they just want you to think dynamically. Determine the x-intercepts of the following. Okay, that's when all these things are equal to 0. Round to 2 decimal places if necessary, which means they might need you to do the quadratic function. I'm not going to do the quadratic function ones, the quadratic formulas, but I will do the solvable ones, one by one. And again, I might have to quit because I have to go pick some things up. Yeah, I have to go pick some things up. So, but I'll do a couple of them, and I'll have to do a part 2 here. So if you look at this one, and you make it equal to 0. 0. So you bring the 2 to the other side. You get 2 is equal to 2 times this. You divide by 2 to get rid of that. So that means 1. 2 divided by 2 is 1, is equal to x plus 3 to the power of 4. You take the 4 root of both sides. The 4 root of 1 is plus or minus 1. So I get plus 1 is equal to it, and minus 1 is equal to it. X plus 3. And x plus 3. So you can see one of the x's, when I isolate it here, x is going to be equal to 2, which means the spot is 2 comma 0. And the other one is clearly going to be minus 4 comma 0. So those are the two x values, x-intercepts of this particular graph. And you simply make it equal to 0 and then solve for x. Now just to make sure. Yeah, right there. Oh, I got minus 2, minus 4. Is that what I had? No, I had, yeah, all I did was a subtraction thing wrong here. Minus 1 minus 3 should have been minus 2, not 2. So just make sure you do you don't rush it like me. So let's look at the next one. You simply set this to 0. So I'm not going to write in the cube root. I'm just going to write in. So you set it to 0. Now how do you solve this? You have to go in reverse bedmass. You can't solve the bracket first. And reverse bedmass says I have to get rid of the 8 first. So I'm going to add 8 to both sides. I'm going to add 8 to both sides. So I'm left with 8 on this left side. And these cancel out here. Then I have to take the cube root of 8, or take cube root on both sides to get rid of this power of 3. If I take the cube root of 8 on this left side, there's two possible cube roots of 8, minus 2 and positive 2, which means I'm left with minus 2 is equal to x minus 2. and minus 2 is equal to, and plus 2 is equal to x minus 2. To get rid of the 2 here, I add 2 to both sides. 2 plus 2 on this left side is 0. And these cancel out. So on that side it's 0. And did I get it right? Yeah, and then this side, when I add 2 to both sides, I get x is equal to 4. Which means my two possible intercepts are 0, 0, so it goes through origin. And 4, 0, which makes sense because if you look very clearly, oh no, it doesn't make sense at all. So, no, it sort of makes sense anyway. I won't explain why that 0, 0 is there, but you can see that just simply setting it to 0, you can solve it. When you can't solve it, that's when you have to pull out the calculator to solve the cube root. So, if this is 0 here, I have to subtract 48 on both sides. So I get minus 48 on the left side, cancels out on the right side, is equal to minus 3 x plus 1 to the power 4. The next thing I have to solve is I have to divide both sides by minus 3. 48 divided by minus 3 is 16, positive 16. So I get that. When I take the cube root of 16, or 4 root of 16, there are two possible answers, possible minus 2 and negative 2. And if you don't believe me, try it out. Did I get that last one right? I wish I'd kept it around. Yeah, cube root of 8 is plus 2 or minus 2. No. Actually, that last one I got wrong. There's only one possible answer for cube root of 8. Cube root of 8 can only be positive 2. Yeah, because the cube root of minus 8 is negative. So anyway, it's only when you take even roots that you get negative numbers. So this is possible here, so I get x plus 1, which means when I solve it, x is equal to 1. And then down here, when it's x plus 1, when I solve it, minus 3 is equal to x, which means it's minus 3, 0, and 1, 0. And if you go to the answers, you will indeed find that. So there's that. Yeah, you see the cube, that one I did incorrectly. There can only be a positive answer for that one. So 4, 0 is the only possible answer. But anything with a 4 root, 6 root, square root, 8 root, there's two possible answers. One is plus and one is minus. So then this one says no x-intercepts, so it's probably going to be the square root of a negative number. So let's have a look. When we set this equal to 0 on the left side, we have to add 10 to both sides. And I'm left with 10 is equal to negative 5 x plus 6 to the power 4. Then I have to divide both sides by negative 5. So I'm left with negative 2 is equal to x plus 6 to the power of 4. Now here's the problem. You can only take a cube root or an odd root of negative 2 to get an answer. There's no possible square root, 4 root, 8 root possible that you can do of negative 2, which is why when we do the next step, which is take a 4 root of both sides, so you're taking a 4 root, and a 4 root here, there's no possible answer there. There's no possible value of x that can go into this square root that would create a minus 2. That's because you can't take a square root or a 4 root or a 6 root or an 8 root or a 10 root of a negative number. Then you would keep going. It's the same process over and over again. You set your y to 0. You've got to add 12 to both sides. And you get 4 and whatever's in the bracket. I'm just going to leave the bracket. Then when I divide both sides by 4, I get 3 is equal to x minus 8 to the power of 4. To the power of 4. And what do I do here? I take a 4 root of both sides. So 4 root of 3 is equal to x minus 8. And the negative 4 root of 3 is equal to x minus 8. When I add to both sides, I get 4 root of 3 plus 8 is equal to x, and that's keeping it very accurate. And then this one becomes 8 minus the 4 root of 3. So written down in your book, you should see this. something like a 3 with a 4 in it plus 8 is equal to x. And they might, since it says up here round to 2 decimals, you'll take the 4 root of 3 and add 8 to it. And then the other answer is 4 minus the 4 root of 3 is equal to x. If I wanted to keep it very accurate, I would leave it exactly like this. We'll do this second one down here, and we'll do 8 minus the 4 root and I get 6.68. So I'll just check one of these answers to make sure it's right. And we can see, yeah, there it is, 6.68. So obviously when I add the 4 root, I'm going to get 9.32, which is the same distance on either side of 8. Just adding the square root, the 4 root of 3, and subtracting the 4 root of 3. And then the next one, same deal. Set this to equal to 0. You got to get 20 to the other side. So you're going to get 20 is equal to 2x plus 5 to the power 3, and then you got to take, there can only be a positive answer here because you can't have a negative cube root that comes out to this, so you just take the cube root of 20. What's the cube root of 20? We'll take it to 4 decimals. Right there. 2.7144. 2.7144 is equal to 2x plus 5. So 2x is equal to negative, and then we're going to subtract 5 from it. We're going to highlight it, add it. And then when I divide that by 2, then we're going to round it up. 1.14 negative. And you check your answers, and sure enough, you get, oh, I did an error there. So let's go back. Was it indeed a cube root? Yeah, cube root. So I have to take, look at that. Negative. So after it became plus 20, I had to divide it by negative. And that means I'm not taking the cube root of 20, I'm taking the cube root of negative 20, which does have a negative answer. Then when I take the negative 5, it's actually negative 7.7144, and that's what I have to divide by 2. And that should get me the answer. So I just didn't see that negative multiplier. Yeah. And will I have to stop here? I'm probably going to have to stop because there's a good 5 more questions. Okay, well, you know, I'm going to do these next time and see if I can do 10 and 11 and stop there. Because extension is more depending on what kind of class you're taking, and there are also things that you should probably go over with your professor. Okay, do this. All right, let's have a look. Go there. You have a function like this, and we don't know what it's a power to. How many zeros will the function have as n is equal to 3? Well, any cube root can only go through the axis. Well, no, that's not true. I can go through the axis 3 times, 2 times, and minimum 1 time. Now, if it's the actual 3, and it's been translated 4 to the right and 1 up, so if I think of the graph like that, this is the parent, because it's been translated 1 up and 4 to the right, it's really going to have 1, because the whole thing has been raised. Really squiggly ones, which is possible when this is not the same cube root. When you have 3 separate cube roots, you can have really squiggly ones that cross the x-axis. But when the root's only the same, it means it only goes through the x-axis once. If you raise it or lower it, it can still only go through once. How many zeros will the function have as n is 4? Well, okay, so since it's raised 1 and it's a positive integer in front, it will have 0 because it never crosses the x-axis. Make a general statement about the number of zeros that the function will have for any value of n and explain your reasoning. Okay, so any even value of n will have no zeros because it's a positive, because there's no reflection, and it's been vertically translated up 1. Normal even functions would only have one X-intercept in this case, because they're all the same root. Any odd value of n will only have 1 0, because odd values must pass through x axis once, and this one has been raised. Is no exception, I guess. Raised once, lower once, it doesn't matter. So let's see what they say as an answer. They say it only has one solution. Then it has no solutions. When n is odd, since an odd root results in only one value. 0 when n is even, since there's no value for an even root of a negative number. Well, okay, they're essentially solving for this each time. But my logic, based on the translations, is the same answer. And then finally, the last one, number 12. Oh, number 11. How did I lose that one? So number 11 says, for what values of n for the function x to the n in the x-axis be the same as its reflection in the y-axis? Yuck. For what values will reflection be different? Explain. For what values of n will the reflection of the function in the x-axis be the same as the y-axis? So this case, you got to think of odd functions. So it doesn't matter if it's odd. If I reflex it in the y-axis, you will not have the same function. But if it's an even function, a reflection in the y-axis will have the same function every time. If it's an odd, a reflection in the will never. So only even functions will have the same reflection in the y-axis. And you will never have a odd function. Okay, when will it be different? When it's odd. When will it be the same? When it's even. There's my answer. Yeah. The reflection of the function in the x-axis will be the same as its reflection in the y-axis for odd numbers of n. Okay, I see. So when will the reflection in the x look the same? Yeah, well, we already covered that, actually, when I showed you that x to the 3, when I put minus out here, looked as the same as when I put a minus in here. See, they look the same. And it's simply because one is actually reflecting in the x-axis, one is actually reflecting in the y-axis, but you can't tell. Whereas when it's an even function, they look vastly different. So I confused the question. But if I was just going to reflect in the y-axis for an even function, you would not be able to tell it's the same if it's changed. So I just misunderstood the question. And then this last one, I don't think I'm going to do it, but so this last one for z, consider the function. Ugh, no. Use algebraic and graphical examples to describe all the transformation could be applied to this function. Explain why just creating a single table of values is not always the best way to sketch a graph. Jesus. Well, you can do reflections in X, reflections in Y, vertical translations up, vertical translations down, vertical stretches, vertical compressions, horizontal translations right, horizontal translations left, and finally horizontal stretches and horizontal compressions. So that's pretty much every one. And then, I mean, algebraically, you'd use Desmos and just keep changing your A, K, C, and D. And I'm not going to answer with B. These kind of hypotheticals, I don't quite understand what they're getting at. So there you go.